So welcome everyone. Thank you very much for joining. This is our 10th webinar within the EC Data Science Distinguished Series. Before presenting our speaker today, let me just briefly go over some logistics. If you have any questions, you can write them in the Q&A chat, and towards the end of the talk, we're going to select some of those to be answered by our speaker. During the talk, I'll also monitor the Q&A in case there's any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of those towards the end. The talk will also be recorded and uploaded to our YouTube channel for future access. So that being said, it is my pleasure to present today Professor Asu Ozdaglar as our distinguished speaker for the data science seminar. Asu received her bachelor's degree from the Middle East Technical University in Turkey in 1996, and her master's and PhD degrees from MIT in 1998 and 2003, respectively. At that point, she joined MIT as a faculty member. 5 years later, she had tenure, and 4 more years, she was a full professor. So that means, Asu, that you went from PhD student to full professor at MIT in less than a decade, which is an incredible achievement in and of itself. She currently holds the position of Distinguished Professor of Engineering in ECS at MIT. She's also the department head of ECS and the Deputy Dean of Academics in the Schwarzman College of Computing. Her research expertise includes optimization theory, distributed optimization and control, and network analysis. Her awards include a Microsoft Fellowship, NSF Career, 2008 Donald P. Ekman Award of the American Automatic Control Council, Class of 1943 Career Development Chair, inaugural Stephen and Renee Innovation Fellowship, and 2014 SPIDA Teaching Award. On a personal note, I had the luck to collaborate with Asu on a project during my time there at MIT as a postdoc, an experience that marked me quite a bit. And as you probably don't even remember this, but we had a meeting to discuss the manuscript in your office. And I thought that it was going to be more of a high-level staff discussion. And you actually took out from your drawer a printed version of the draft with annotations. And we were going over each line, kind of discussing the meaning of a specific line. So since then, right now that I became a faculty member, right, since then, whenever I think that I don't have time to go in detail over my students' work, I just think, if the department head of MIT has time for this, what's my excuse, right? So that was very, very much marked me. So Asu, thank you very much for spending the afternoon with us. We're very glad to have you here, and the floor is all yours.
Thank you, Santiago, for the incredibly nice introduction and the invitation. I'm super happy to be here with all the challenges. I'm so grateful that we have the Zoom, at least, that will allow us to connect this way. Actually, this made giving talks much easier than the usual time. So there are some very little benefits of our current unfortunate situation. But I'm very delighted to be with you. I can't see you, but I can see Santiago, so I'm very happy. And today I'm going to talk about min-max optimization. It's a topic that's very dear to my heart, one that I actually used to work as a PhD student, and now, sort of rekindled interest, mainly because there's a lot of attention, recent attention in this topic, motivated by robustness issues, as well as generative models in machine learning. So I'll basically try to argue in today's talk that min-max formulations provide a sort of a canonical backbone for addressing these issues. And I'll talk about, some of our past work and as well as some of our recent work, what gets us excited in this area, and sort of focusing on some algorithmic progress, systematic insights, and then performance guarantees. And before I forget, this is a joint work with some brilliant people, Farzan Farnia, who's a postdoc at MIT right now, Sharat Patatel, who's a graduate student, responsible for much of the work, and then Aryan Mokhtari, who also was a postdoc, but now a professor at UT Austin. So much of the parts of the work is joined with these fantastic people. So let me get to it. And, essentially the problem we're interested in is a min-max problem. We have a function f of 2 variables, x and y, and I'm not even going to talk about constraints over them. We're interested in minimizing this function over x and maximizing over y simultaneously. And these arise in many applications in optimization. Let me start from optimization. And this is how applications look in optimization. So it's basically worst case design is one that robust optimization is a place where we're basically viewing y as a parameter and we're minimizing our cost function decision vector x, assuming the worst possible value of that parameter. The other place, which sort of why I was interested, I mentioned as a PhD student, was basically it's also the underpinning of the duality theory for constraint optimization. So the idea is basically we have a constraint optimization problem, minimize f of x, subject to a bunch of constraints, j of x, j from 1 to n. Now, to solve this constraint problem, we generally form the Lagrangian function, which is f of x plus some Lagrange multipliers gj of x, and then we consider the dual problem, which involves minimizing this Lagrangian over x, which gives us a dual function, and which has much nicer properties than the original primal function, and then we maximize that dual function over mu. So this is how a very generic way of both formulating and also designing algorithms for solving such constraint problems. And as you see, this is also a max-min, but we can also write it as a min-max problem, but it is a min-max problem. So the interest here in the min-max problems as a solution concept is finding a saddle point, or I'll use these terms interchangeably, stationary point, Nash equilibrium of this function f, and that's basically a pair x star y star such that f of x star y star, when you fix y star, is less in cost value for any x and greater if you fix x star when you think about variations from y star to any y. So this is basically the Nash equilibrium as we know it, right? You think about unilateral deviations and you can't improve your function value. And the standard method for computing these saddle points is this gradient descent ascent. So what you do is you're trying to minimize in x, maximize in y simultaneously. So what you do is you take simultaneous steps in x and y, a descent step along x, gradient of f with respect to x, and an ascent step of gradient of f with respect to y. So when I started working on it, I wanted to see what literature is available on sort of these kinds of algorithms. And you can actually find some very interesting literature going back to 50s and 60s on this. And I was very mesmerized by reading these papers. These are actually very interesting because it's not optimization literature. This is coming from mathematical economics. So Arrow Hervis Ozawa has a beautiful edited volume, a book that actually focuses on mostly these kinds of methods. They focus on they study continuous time versions of these models and improve some stability results under strict convexity assumptions. And you look at Ozawa, who looks at the discrete time version. Again, you see strong convexity assumptions. You try a little bit more. They tried sort of relaxing the strong convexity, but I would say not, too much. There's the stability assumption, which essentially amounts to uniqueness of an optimal solution, so it doesn't really fit into the problems that we're considering here. So while I was actually looking at these, I found a paper that I read. This is the Goldstein when I was, a grad student, and I wanted to share with you the remarks I put here. Sort of, this is the strong convexity or stability assumption. It's like very restrictive. As I show this slide to students to just say, be critical. Don't worry if it's like a super mathematical, economist. You can still criticize the papers, and that's what actually motivated me and Angelia, my collaborator at the time, to say, can we do something for this problem for the convex case? Can we, relax the strong convexity concavity assumptions? And that sort of this is a paper from very long ago, 2009, maybe more. I mean, that's the publication time of the paper. So what we did is basically, this is a very nice trick in trying to get convergence rate for these kinds of algorithms. We considered ergodic iterates or time averaged iterates, and under the assumption that subgradients are uniformly bounded by L, we were able to show that without strong convexity concavity, you can show convergence rate results for this algorithm that I just shared with you, which is basically 1 over n, sublinear that converges at rate 1 over n, but also delta is the step size. So you also have some error neighborhood. You converge to an error neighborhood. If you want to converge exactly, you have to use a diminishing step size, which will basically then lead to a lower rate. Anyway, I think this is sort of was our attempt in 2009. I was very excited in these problems, and we felt like this gave a convergence rate guarantee without strong convexity. Of course, boundedness assumption is restrictive here. It needs something like the variables to be in compact domains, and for optimization problems, I mean, for the duality case, you have to do a little more, but for many of the optimization problems we were considering, this bounds made sense. So we basically were satisfied with this result. So fast forward 15 years, the pictures became much more colorful. So, you know, I showed you applications in optimization. This is applications in machine learning. And basically, the reason I got interested again in this was, first of all, adversarial robustness. But we sort of, you can find many examples, I think, adversarial examples in many talks. This is one that my colleague Alexander Madri uses, and I like it, so I'd like to share it with you here. So this is sort of a picture of a pig, and you use a state-of-the-art classifier that actually classifies it as pig with 91% accuracy, and you add some very small, imperceptible adversarial example. It's not really noise, so it's carefully designed. Then you classify it as an airliner. So this is sort of machine learning makes pigs fly example. I showed this to my son. Actually, this is his favorite example. After this, he's 8 years old. He's like, I want to be a machine learning person when I grow up. So this is, I mean, this is very colorful, makes people very interested in these problems. And then basically, if you look at, you know, joking aside, how do we formulate this problem? So standard training, think about, you know, let's think about the standard classification setting. We have some probability distribution over the pairs, W theta. W is the input images, input theta. Theta are the corresponding labels. And we want to select, we have a model parameterized by this X, and we want to select these model parameters to minimize some expected loss function. And in the robust case, as opposed to standard, we also want to consider the inputs W to be adversarially perturbed. And in this sort of paper by Madri et al., they assume L-infinity perturbations of the data points. So it's a very good question. How do we think about perturbations? Why pixel L-infinity perturbations is the right approach? But, you know, that's an open question we can discuss. Assuming L-infinity is the way we actually represent the perturbations, then the robust learning problem essentially amounts to finding the model parameters to minimize some expected cost as before, but now against the worst case loss, where it's worst case with respect to all allowable perturbations. So we have another min-max formulation that is sort of, you know, forms the basis for understanding how to design defenses against these attacks. So min-max formulations also arise in the context of generative adversarial networks, GANs. This is sort of the goal here is to learn the distribution of the input data using observed samples x1 to xn. And this sort of GAN approach can be formulated as a zero-sum game with two players, two neural networks. There's a generator that's generating some real-like samples from random input. So it's, you know, which is trained using these observed samples, trying to mimic the input distribution. And there's a discriminator, which is basically trying to distinguish generated samples from real samples. And this leads to a min-max problem again, because it's a zero-sum game. And this is Goodfellow's original formulation from 14, minimize over generator, maximize over discriminator, some loss function. Here, I think this discriminator is a classifier. So actually, this is interesting, because why is this distribution learning problem a min-max problem? So one can show, actually, you can show that this objective, maximum objective, is at the optimal discriminator a distance. It's shown to be a distance or a divergence measure between the true distribution and the generated distribution. So what the generator is trying to do is minimize this divergence measure. So for different GAN formulations, this corresponds to different divergence measures. For the Goodfellow one, I think it's Jensen-Shannon divergence. For others, it's different kind of divergence measures. So that's why min-max makes sense. But anyway, that's the background. But the sort of resulting formulation is a min-max formulation, a very tricky one, because so far it was much nicer. You can say something about its convexity property. This is two neural networks. So this is non-convex, non-concave. So both mathematically and empirically, it actually creates a lot of challenges. I will mostly talk about the mathematical challenges, but let me show you the empirical ones before. So the GAN training, sorry, did I pause the share? I did something.
No, we can still see you also.
Sorry, I was trying to move this black line. So there's a lot of challenges in training GANs. GAN training is usually done using these first order methods. You think about, one step of minimization, a couple of steps of maximization. It suffers from this so-called instability. This is the I guess Celebate data set. Your goal is to generate images of people who look like celebrities. You run it for 60,000 iterations. You feel like you're getting something, close to, I guess these look like celebrities. But then you you stop there, you go home and you come back and you see that there's a sort of huge degradation in the algorithm, sort of starts immediately going, degrading in performance the images that are generated. The other sort of problem that is very common in GANs is sort of this notion of mode collapse. And that's basically generating images which lack diversity. So you want to generate these bedroom images using some bedroom images
so at this, sorry, Asu, that I interrupt. So at this point, we're actually still seeing your previous slide. So maybe something happens, right? We're still seeing slide.
Yeah, that said, your screen sharing is paused. So this is another one we have, lack so-called mode collapse, and that's another challenge that we observe empirically. And understanding these things, more in a more principled way is something that got our group quite interested lately. But before even going, so this is all just to show you min-max problems are challenging, more challenging than optimization. There are interesting mathematical structures that can be exploited. Before even going into that sort of fancy examples, I just want to show you, like, even for the simple bilinear case, I presented you the GDA, right? And we're trying to get convergence, stability for training these GANs out of algorithms like GDA. But let's just look at the bilinear problem, like a simple example, x prime y. And the solution here, the saddle point solution is 0, 0. So if you apply actually gradient descent ascent to this problem, you're gonna basically move in xk along gradient of f with respect to x, which is yk in this case, with some step size, and similarly xk, you're ascending in y. And okay, this is very simple, and you can actually write down the iterations and then show that because your eta is positive, this is greater than 1, and you're basically diverging instead of going to 0, 0. This very simple problem, bilinear problem even, fails to converge to where you want to converge. So this is annoying. So how do we deal with this? So this actually made people, especially lately in the last couple of years, consider variations on GDA. But then realize that these variations, I'll tell you the history of all of this, have appeared in the literature in the past as well. But the first recent popular variant is the so-called Optimistic Gradient Descent Ascent, or GDA with negative momentum. And here, basically, the idea is, without the blue part, this is just our original GDA, right? You descend in gradient XF, ascend in gradient YF. So this does something interesting. It has a 2 eta, like a little bit larger step size on this side, and puts an eta step size, and then moves you back along the gradient of the previous iterates. So I saw this first time, I think it was maybe 2 years ago, or maybe 3 years ago. Kostis Daskalakis presented this algorithm, and I was like looking at it, and why would this work? And then Kostis also said something like, well, you have to really pick this step size to be twice that for convergence. So that sort of, is very motivating for me. What is this algorithm doing? I mean, you can actually try to understand the intuition a bit through some, hand-wavy argument. So what this is doing is basically at xkyk, you move in the direction of the gradient, and then you go back in the direction of, xk plus yk plus 1 out, and then you go back with this negative momentum. And instead of these cycles or, things that may diverge, that actually allows you to go inside and then converge to x star y. So that's sort of a very loose sort of idea of why this may work. And okay, I saw it in the Kostis's work. Apparently, this was studied by Sasha Raklin and others in the context of online learning. That's where I taught for a while that, that's the first place it appeared. Actually, this was introduced by Popov in 80s. And it's always about convergence in those papers. There's not much about rates or understanding exact convergence. So, very recent papers, a beautiful paper by Liang and Stokes, and then our paper in GANs is pretty much independent studies that looks at OGDA for bilinear cases, strongly convex, strongly concave cases. So as you see, these algorithms have been out there for many, many years. It's only now that we're trying to sort of get some understanding. But still, this is sort of mysterious to me, why this 2 times that. So I'll try to, I think in this talk, give some intuition, or at least our understanding of how these algorithms work. So just to go back to my previous bilinear example and apply OGDA, you basically, remember it was yk, so it's 2yk minus 1. And if you put it and then analyze, let me not go into the details, very surprisingly, it does go to 0, 0. And okay, so let me also now talk about another algorithm, which is well known, which is the so-called proximal point algorithm. And that's sort of an algorithm which is very similar to GDA, but instead of getting a gradient at xk, yk, it actually looks into the future and gets a gradient at xk plus 1, yk plus 1. So you're basically evaluating the gradient instead of xk, yk at xk plus 1, yk plus 1. And for this simple problem, you can, rearrange the terms and then get an exact update for xk plus 1. Otherwise, it's sort of it requires an operator immersion here, right? So it's not really easy to implement in general. I view this as much more of a benchmark, or it's like it has very nicely, when you study this, it has very nice convergence properties, but it's not implementable. So if you think about running proximal point here, it also has some nice convergence, and we actually can compare OGDA and proximal point and see that what OGDA is doing is very actually similar to what proximal point is doing. So their paths are very similar. So that was the first realization when we were trying to understand OGDA. And that's sort of what I'll try to highlight in the first part of the talk here. Basically, view OGDA as an approximation of proximal point and use that idea to show that, OGDA actually, even in the convex-concave case, has a convergence rate of 1/n. I will also show another popular method, extra gradient, which is very different looking than OGDA, but I will basically say that we can also view this as an approximation of proximal point and then get a rate result for that. I will say a little bit about all of these things I talk about are, again, convergence rate results with these ergodic averages. You take the time average of the iterates. And there's some recent also interest in last iterate convergence of these algorithms. And I'll try to highlight why people are interested in that. I've been to many talks and I was like, why are you interested in last iterate convergence? We already have the ergodic average, right? But I'll try to argue why people have been interested in this. And I'll basically show that, present some convergence rate results for last iterate convergence and show that it's probably inferior to ergodic iterates in these algorithms in the convex-concave settings. And finally, I'll go back to the GAN training, which is, this is all convex-concave so far. I'll go back to the nasty case of GAN training, and I'll try to say, can we do something about these instabilities that we're observing and maybe come up with some new equilibrium notions and stable training algorithms. So that's sort of the plan of the rest of the talk. Okay, I hope the outline is clear. I will go into sort of more of the details now. So we're thinking about, again, this is a little bit putting things, maybe repeating things, but we're interested in a saddle point throughout of this f of xy. Throughout the talk, I'll be interested in the convex-concave case. I will also assume some nice, smoothness properties. I will assume this f is continuously differentiable. The gradients are smooth. Lipschitz, the function itself is smooth. So in the sense, gradients are Lipschitz with some Lipschitz constant L. And I've already said what we mean by a saddle point. Now, the proximal point, which I talked about, right, which I said it's actually evaluating the gradients at xk plus 1, yk plus 1, the more, sort of typical way of expressing that algorithm is basically this. I mean, you min-max f of xy, and you introduce some regularization around the previous points. Sort of, I think there's a lot on proximal point minimization, less so on min-max, but there are some papers on that as well. But I mean, if you look at this, it's almost like as hard as solving the original problem, right? You have to maximize f of x plus some quadratic penalty. But anyway, let's just put it as a benchmark algorithm. And it's not too hard to show that this actually iterates these ergodic iterates of this algorithm satisfy some 1/n convergence rate result. I'm not going to go into this because I'll just give you the more general case for the OGDA in a second. So here is, I think, what when I realized this, found very interesting. So one way of approximating, so remember OGDA was you get a gradient at xk plus 1, yk plus 1. So we can actually think about approximating this xk plus 1, yk plus 1 as xk yk plus xk yk minus xk minus 1, yk minus 1, right? Sort of that's one way I can use to approximate this gradient at the next step. And this actually, if you plug in this approximation to the OGDA update, which gives you an implementable algorithm, because now this is in terms of the current and past iterates, not the future iterates. This now is exactly the OGDA update. So this is what I was trying to argue through this example. This is actually can be viewed as an approximation of the proximal point algorithm. And that exactly is the idea we used to get the first convergence rate guarantee for OGDA in the convex-concave setting. It's basically the same complexity estimate as the proximal point. It's 1/n, okay? And I want to just quickly tell you, let me make sure I'm doing okay with time. So how do we show such a rate estimate for these algorithms? So we analyze it as a proximal point method with error, right? So this is, remember, OGDA, but it's I showed you basically we can view this as a proximal point iteration, but with some error. And I'm going to use some notation here. I'll just put these gradient operators into this capital F and the errors into epsilon. And epsilon, the error for OGDA is exactly, can be written like this. Okay, and this is something that one can actually convince in a second. So this is how we view the OGDA. And to analyze this, we basically go through this key lemma. I mean, the analysis of Minmax, it's interesting to go over this because it's a bit different from the usual gradient methods analysis, either in terms of, objective value function or distance to the optimal. So it really goes through this, I always remember this as three-term lemma. And because this has now error, we also introduced an error. So if you have this proximal point with error, this is the three-term equality with error. It's not too hard to derive this, but this is the key lemma we will be using to analyze OGDA. And once I have this lemma, basically what I will do is I will add the right-hand side for overall K. I will basically substitute the OGDA error, massage the terms a bit, and I get this kind of inequality here, okay? I want to give you sort of the main idea of how we can get convergence rate results for these min-max type algorithms. And once you have this, I mean, this sort of, because we added over 0 to n minus 1, as you see, these things telescope. So you get z0 and zn, and all the other terms disappear. And you have this function value here. And I will use here the Lipschitz continuity of f to write this as zn minus dn minus 1 times dn minus d norms. And then do some massaging with the rest of the terms to be able to get this result here. But we're very close. Once we have this, we're very close to the end. One thing I can see immediately from here is, because this is monotone, I mean, this comes from convex concavity, right? Gradients, this is the gradients of f with respect to x and y. So this makes, by convexity, this inner product non-negative. So this side is non-negative. So if I put Zn on the other side, this immediately gives me that the iterates are bounded. So this is one way one can see, obtain that the iterates that are generated by these algorithms is bounded. This is a big deal because many of the papers actually assume that the iterates are bounded and do some analysis. This is just showing that you can get the boundedness. And this is actually the reason. Remember, GDA was diverging. So OGDA, whatever structure it has, immediately leads to iterates that are bounded. So the next step is, this averaging here will give me, this is the trick why we get all these results for ergodic averages is using sort of the convexity concavity, I basically get a lower bound on this estimate as a function of the function values. Now these are sums over f of x, k, y, and using the convexity, what I can do is this is greater than or equal to f of average of xk's, and that's exactly my ergodic average. And I do the same thing for y. So that gives me immediately an estimate of the function values of the ergodic averages. And then basically I'm almost done. I just put some bounds on z0 minus d, zn minus d. I established they're bounded by some d. And if I divide this side by 1 over n, I immediately get the 1 over n result, rate result. So it's a combination of three things, right? Three tricks that I used. Basically, I went from here, function values to the function value at the ergodic iterate, and then I used the boundedness of the right-hand side to be able to get a rate result as a function of 1 over n. So that sort of completes the proof. There are some details I'm missing, but I hope I was able to convey some of the main ideas of how you analyze these algorithms. Okay, so that's OGDA. And then this is another method that people use in now GAN training. I mean, we use I worked on extra gradient way long ago, but this seems to be popping up now. And this is again an algorithm from '77 by Korpelevich, and it's a modification of gradient method, uses the idea of extrapolation. And I will show you, and this is going to, this is why I think I got so excited about all these things, because they look so different and their analysis are different in different papers. So what's extra gradient now? So remember it as it's also trying to look into the future. And how it is doing that? Well, you're at xk, yk. You move in the gradient direction. You're at xk. You move in the gradient direction. You create this midpoint. And then you look at the gradient at that midpoint. You go back to xk. You take a gradient with respect to that midpoint. That's what is extra gradient. And somehow this is also very stable. And it's beautiful, except, why, like OGDA was doing something else, this is doing something else. So that's another thing that sort of got us thinking for a couple months. And we realized actually that you can write down the EG update if you play with it a little bit, like follows. I'm not going to show this, but this is not too hard to see. You can write it as an evolution over the midpoint iterates, right? This is the k minus 1/2. This is k minus 1/2 and some stuff. And I argued, I will just try to show you that this is actually an approximation of a proximal point algorithm on the midpoint iterates. Meaning, look at this part now. This is basically an approximation of k plus 1/2, because it's k minus 1/2, yk minus 1/2, plus, how much you move from k minus 1 to k. So that gives you basically an, approximation of the gradient at k plus 1/2. So if you plug this approximation here, this is exactly how proximal point operates over the midpoints. So EG is basically just like OGDA, an approximation of the proximal point with a very similar idea. One of them goes on the point itself, and the EG goes on the midpoints. And that's sort of, that's exactly what you need. Rest follows, okay? So you can actually get a little bit more constants and stuff, but the same 1 over n complexity. And let me compare also our results now with sort of Nemirovsky's seminal paper. He also considered convex-concave case for EG extra gradient, and he assumed feasible set is compact to get this result. There's another paper by Montero and Sweeter in 10, which extended these results on bounded sets, but not with F stars and using a very different termination criterion in terms of the norm on the gradient. So basically our result shows a convergence rate on the function value without assuming compactness. So you don't need compactness to be. And it all comes from sort of viewing these very seemingly different algorithms as proximal point algorithms. So that's the one message I think I want to. There's many algorithms, the gradient type algorithms going out there right now, used in sort of several different problems. I think this sort of gives at least some calmness to me that I understand where these algorithms are coming from. So let me now move on to this last iterate convergence business, because we've always done many of our analysis in this convex-concave case in terms of these ergodic iterates, as I mentioned. And there's been sort of some interest in studying last iterate convergence. And so I've been going to some talks, people are talking about last iterates, and I was always not sure why people are looking at last iterates. And generally the argument goes something like this. We're studying convex-concave case, and you've seen in my analysis how these convex concavity and ergodic iterates marry to be able to get these rate results. If you don't have the convex concave case, which is our goal, we want to actually be able to have an understanding for the non-convex, non-concave problems. So you actually want to get guarantees not for the average iterates, because those average iterates in the non-convex, non-concave case may not mean much. We want to get last iterate guarantees for that reason. So that's one reason why we want to be able to get some last iterate guarantees. And the other one is basically that if you want to preserve sparsity for the resulting solutions, we don't want to average everything and combine all the components. Rather, we want to actually be able to get with some without combinations for the last iterate. So that was the motivation. But I've always felt I was so happy to get this result. So this basically, what this shows is that the last iterate of the extra gradient algorithm is actually slower than the ergodic iterates. It's 1 over square root n. And this is basically, to our knowledge, the first characterization of the convergence rate of the last iterate. This is joined with Sharat and another brilliant student of Kostis, Noah Golovic. And this is for the general convex concave setting. And so this is an upper bound, right? This doesn't say necessarily that this is slower, but I will show you in a second that we also have a lower bound that matches it, showing that it's probably inferior to the ergodic averages. So the proof for this, basically I put it here. I'll just quickly say something about it. It again goes through the 3-term equality, for these kinds of algorithms. Just out of this talk, please just remember 3-term equality. So it's this sort of 3 terms. And now again, using monotonicity, this is greater than or equal to 0. Forget the negative term. Zk plus 1 minus dk is f of zk. Move this to the other side. This side is bounded. You immediately get that the sum of this guy, norm square of f, is bounded from above by d square over 2 eta. So if that's the case, that means the minimum of this term, let's say some k star, is less than d square over eta square n. There exists some k star between 0 and n minus 1 for which this is true. Now you can show for proximal point algorithm that this function sort of is like a Lyapunov function. It's decreasing, implying that not just k star, but the last n also satisfies this. Okay, so this is an easy proof for proximal point, easy proof for getting a last iterate convergence for proximal point. For EG, it's not as easy. It requires a lot of algebra. I mean, this is like, I was amazed how these guys did it. But basically, it goes through just noting that even though this does not decrease with EG, it does not increase too much after k star. So you can still get this 1 over n rate for the EG iterates. Okay. Okay. So this is great. I was actually very happy to see because I've always, as I said, worked with ergodic iterates before for convergence rate results. This is the sort of I thought another thing I want to highlight because I felt like it came together nicely. We were also able to get a lower bound, and lower bounds are tricky. It generally, uses this first order oracle model of Nemirovsky and Yudin. So as I mentioned, upper bound establishes a quadratic separation between the ergodic and average iterates. We show it's tight by using the stationary canonical linear iterative algorithm framework. Beautiful papers by Arjavani, Shamir, and Azizian. And basically, the key idea here is, the first order oracle model is generally used for quantifying computational hardness of optimization problems. And the idea is most of the time, basically, it models, this approach models the way the algorithm acquires information about the function, right? It's basically sort of assumes some interaction of the algorithm with a black box first order oracle, right? It keeps sort of getting first order information at the current points of the function. Instead, we use a structure-based approach that is sort of presented by Arjavani and Shamir, which assumes certain dynamics for generating new iterates. So assume the iterates are generated by this class of dynamics. And this includes large family of first order algorithms. And moreover, when applied to quadratic functions, it actually reduces to applying a fixed linear operator or fixed linear operator recursively to the generated points. And this now enables, instead of these, trying to sort of span the whole space type of arguments, which turn out to be dimension dependent, enables dimension independent bounds. And basically, using this approach to a bilinear min-max problem, we can show that actually this EG also has a lower bound, which is 1 over square root n, and essentially matching the upper and lower bound and proving that this is basically inferior to thinking about average iterates. So this is, I think, looks like sort of a technical result, but I think it's also very insightful in the sense when you're trying to, so the problem with min-max problems is these oscillations, right? By sort of averaging, doing these time averages, it smooths things out and allows you to make more progress towards the saddle point solution. So I think that's why it's important maybe to think about time average iterates as opposed to the last iterates for this problem. So let me now move on to something a little bit different. And because I started talking about GANs, right? So what do we do with GANs now? And GAN training, remember, was non-convex, non-concave. And the first question, even before the algorithmic question there is, does the saddle point exist, right? We don't have the sort of min-max guarantees, the von Neumann results that says there exists a saddle point in the non-convex, non-concave case. So the first question is, does Nash equilibrium exist? My answer to this for a non-convex, non-concave problem generally would be no. And we have a number of recent papers that actually show that for the non-convex, non-concave functions in general, we don't have a saddle point solution. So we basically wanted to ask the same question for GANs with Farzan. And it's well known in this GANs literature. People generally say, oh yes, under the realizability assumption, there exists a saddle point. And what is that realizability assumption? Well, that's basically saying that you have a generator that's so rich, expressive enough that it can actually match the input distribution, right? That's the realizability. And if you have this assumption, it's not too hard to show that this G star together with a constant discriminator gives you a Nash equilibrium. Now, okay, so that's the assumption that people go with. There exists an equilibrium in this, right? But then if you actually write down some GANs, simple GANs, like let's assume the generator is linear, for instance, you can immediately show that for the non-realizable GANs, you do not have Nash equilibrium. For instance, this is our simple example I just wanted to put here from this paper. So assume the input distribution we're generating, we're trying to mimic is a Gaussian with zero mean and sigma square, sigma greater than 1 variance. And we have a regularized generator, linear, and we assume that A and B are less than 1. And we basically feed zero mean, identity variance, noise to this generator. These have no saddle solutions. Now, the paper has the proof, but I wanted to just put 2 lines to show why that may not be. And now think about it. The G of Z is you feed Z normal 0 identity. G of Z is mean B, right? And covariance AA transpose. And you're trying to mimic X, which is sigma square I with sigma greater than 1. Okay, so you play with it a little bit, and you, as I mentioned, the min-max formulation actually minimizes the distance between the distributions, these 2 distributions. So if you write it as a minimizing the distance between distributions, you can convince yourself that you need to match the mean. B star is equal to 0. And then you show that the GAN objective at the optimal discriminator is concave as a function of B. So it's something like that. And if you want to minimize that, a concave function, that has to be at the boundaries, not interior. So using some argument like this, you can show that basically there does not exist a saddle point. And this is an example though, this is just a very specific generator, right? Then the next question one asks is, how about for standard architectures that people use in GAN training? Does this saddle point exist? And for that, we did this following experiment. We considered a bunch of different commonly used GAN architectures. We trained them to a point, I think 200,000 iterations, and we got some discriminator and generator. And then we fixed the discriminator and then continued to optimize the generator. So if this was a local Nash equilibrium, this wouldn't, you wouldn't be able to improve or, change the performance by much. But what we've seen was as we further optimized the generator, the performance got worse and worse. So this told us, at least, this is not a formal result, but said that where the GAN architectures converge need not be a stationary point. So in order to deal with that issue, we tried to say, okay, this is Nash equilibrium may not exist in the non-realizable case. Can we think about a different equilibrium notion? And for that, this is again going back to this is sort of, I guess, the proximal ideas. We introduced a proximal objective, which sort of gets our original f of xy, but regularizes the original objective by allowing allowing some room for the discriminator to optimize in a ball, so that it's more sort of robust to perturbations of the generator. So think about the previous example, right? So this was, if when we perturb the generator, discriminator was, degrading significantly. So this allows us to regularize that objective and gives us a bit of a room to be optimal against the perturbed x. So we get this proximal objective and consider the saddle point of this proximal objective and call it a lambda proximal equilibrium. And interestingly, when lambda is equal to 0, okay, you get rid of this part, and proximal equilibrium essentially reduces to what we call, in game theory, a Stackelberg equilibrium. If you put lambda equals 0, so what that means, that if you write down the min-max with over x and y of this objective, what that amounts to is minimize over x, the maximum, lambda is 0, the maximum of y f of xy. So x minimizes, assuming that y will take the worst value, and y star is the argmax of f of x star y. Okay? Now this is exactly how, if you actually have a sequential game as opposed to a simultaneous move, in which the generator moves first and then the discriminator takes an action in response as an optimal action to whatever the generator does. Now the generator knows the discriminator will act optimally, right? So that's exactly the two-stage game. So it captures in some way the sequential nature of GANs. This is always easier in terms of existence than Nash equilibrium. This is not simultaneous move, but it's for lambda equals 0. Basically in terms of training, this is actually has more potentially more instability. So what we did in the paper basically is introduce a spectrum of equilibria, all the way from Nash equilibrium for lambda equals infinity to lambda equals 0, which is the Stackelberg equilibrium, and in anything in between. And what we showed is basically that for Wasserstein GANs, for instance, proximal equilibria exists for lambda positive. And this is the usual GDA training for GANs, which does one step of maximization in Y, one step of minimization in X with respect to the usual GAN objective. Here, what we did was basically try to optimize this proximal objective. Okay, sort of the steps are not too important, but just get the proximal objective that I just defined here and do min-max over this. Okay, and then the way we do it is we basically take t steps to find the maximum of this, and then do the minimization instead of a descent ascent. We maximize the prox by t steps and then take a minimization for the outer step. So if we actually do that and repeat the experiment that I showed you before, the proximal training seems to be converging to a more stationary solution. Meaning, if I actually fix the discriminator and then optimize the generator, I don't actually see that huge degradation in performance. And similarly, we did some other experiments to actually compare what we get from regular gradient training versus proximal training. And you seem to be getting some more, this is just qualitative, some more celebrity-like images as opposed to some of these corner cases here. And, to get a little bit more quantitative understanding of whether you're improving or not, we use this so-called inception score to actually, look at our generated data set and then, basically pass that through neural networks to be able to get some idea of sharpness and diversity. That's sort of a quantity that measures both. And we see here some, something like a 0.5 improvement, which Farzan has convinced me that it's a big improvement for GANs of this nature. So that sort of, I think, concludes the talk. I try to sort of highlight to you that, this Minmax stuff is old, even older than me. But I think there's a lot of potential, both in terms of, it used to be Minmax optimization, but I now view it as Minmax learning. So there's a lot of things to actually, understand, use its structure of the problem to be able to get both algorithms and, results that we will hopefully get more understanding of. So these are a couple of papers that I talked about, and with that, let me thank and see if there are any questions.
Yes, thank you a lot, Asu. So very instructive. I learned a lot, and I think everyone attending the talk learned a lot. It's very
Should I stop sharing so that I see people, or?
Well, but maybe you can use your slide to answer some of the questions.
Okay. Yeah.
So actually, we have a few coming in. So remember, everyone, you can write in the Q&A chat. So the first question, so Zach Pitkow, he's asking, can you speak about second-order optimization methods? For example, how do convergence properties change for second-order methods for minimax problems?
Yeah, so we haven't looked. There's some work on the second-order methods. We haven't looked a lot, mainly because it's harder to get rate results in the second-order case. I think that's still an ongoing work, open set of questions there, I would say. So I don't think we have an understanding that it improves things as it does in optimization. For min-max, it's more challenging. There's just a lot of open questions there that one should explore. But it's not clear to me that we will get improvements in rates and things like that as we do in minimization.
Okay. So Zach actually asked another one more on the GAN side. He asked, if we impose a norm constraint on the GAN solution, then we have no boundary on the optimization domain. Do we obtain saddle optima in that case?
Maybe let me try to understand this question.
Yeah, so maybe also
it already has a bound on B. So that's...
So Zach, I just allow you to talk there. If you want, you can explain a bit more.
Thanks, Santiago.
Of course.
Okay.
I can't see him. I can just see his name. Hi, Zach.
Hi, Asu. Beautiful talk. Thank you so much. So you were saying that you get pushed to the boundary for these optimizations, right? Mm-hmm. So there are no interior solutions. I'm wondering if you restrict the optimization to that boundary, for example, by putting a norm constraint on the image that you're optimizing over, then there's no boundary to push to. It's just a question of the angle. Which particular angle do you take? And we've mm-hmm. used that in some optimizations before. Mm-hmm. So then I'm wondering if you get a saddle point solution there's only interior points then. Mm-hmm. And I'm wondering
maybe we do in that case, Zach, but here the goal was to show for, reasonable, like norms, the regularized settings. Is it possible to have cases where we don't have it? I mean, in the case you're mentioning, you're right. I don't think our proof works for that. But I think the point is there's a large set of cases where we don't have these saddle points. So that's one. And the other one that I think motivated us also a lot was this sort of experiments that we were running, right? So this is showing us that you don't have even the approximate Nash, right? You don't get, these are sort of, we tried it for a number of different, and the paper details it in a number of different GAN architectures. And whatever we, in many of the things that we tried, we actually saw that things degrade. So they're telling us that this does not really converge to a approximate, not even local, because these algorithms do local steps, local Nash equilibria.
So those pictures that look like monsters at the bottom,
I know, it's
are the
super
magnitudes
creepy.
growing?
What's that?
Are the magnitudes growing of those pictures as well?
I don't know. I don't know the answer to that, Zach. I'm happy to check with Farzan and get back to you on that, but I don't know.
Because that could be one. I mean, we've seen that.
I know what you're getting at, like by sort of trying to bound this, can we avoid this? I think I don't know the answer to that.
Thank you very much.
Thank you, Zach. Very, very good question. Thanks. So let's see. So people can write. So in the meantime, I can just shoot one myself, right? So you started motivating the idea of GANs with saying, there are two drawbacks. One is instability. One is mode collapse.
Yes.
You talked about solving instability by using this.
Yes.
Do you have something to say about mode collapse?
Yes. We're working on it actually, and trying to understand. There's interesting things there as well, which comes from exactly this min-max structure, and because you're doing the non-convex, non-concave case. I mean, I don't know the answer. We're working on it, but there seems to be in special cases at least. I'm happy to talk to you offline, Santiago. This is with Sharat and Farzan. In special cases where actually you can understand why this is converging in the quadratic cases, why it's converging along a particular eigenvector dimension. It's coming very much from the optimization of the min-max problem.
Okay, yeah, that'd be great. Yeah, it'd be very interesting.
So indeed, that's why I actually put them both, but the other one is not out yet.
And then, so I guess a follow-up question on that is, right, so here, what a lot of the things that you're studying is, grabbing these maybe common architectures and saying, look, you can do iterates that take you to a better place, right? Can you revert the question and say, now that you understand some of the iterates better, then redesign the architecture in the first place to have a good fit between the architecture and the iterates? Is there anything there to think about?
That's a great question. We are not doing that, clearly. We're just focusing on, given the architecture, how do you train it? There is, I don't know, but there may be. There may be in terms of if you actually think about designing the algorithm. This sort of, I've looked at a bit, unfolding algorithms, like you use the algorithm to be able to design the architecture. There may be. We haven't done it yet, but it's a very interesting question. Can you think about, an improved algorithm, and you use the improved algorithm as a way of maybe informing how you actually design the architecture itself?
Right. Yeah.
Right?
Exactly.
This is exactly a very interesting question, but I don't know the answer.
Okay. So let's see, we actually still have 2 minutes. That's great. So so something that I was wondering, and this is maybe a little bit more a basic question, but I just maybe you can give me some intuition, right? So you were talking about OGDA, and then looking at negative momentum like one step, and then EG, and looking at this intermediate point. When always I listen to the things, I don't have again too much on the optimization knowledge. When say my question is always, why stop at 2, right? Is it really like you cannot improve if you look at a third?
You cannot. Yeah, that's in our paper. That's a very good question. That's exactly what I exactly wanted to understand these algorithms to be able to answer questions like that. It's not clear at all why you're doing 2 times the, for instance, you don't need to, now our analysis shows that you don't need to do exactly 2 times the step size for the negative momentum versus the other. So that's one thing we wanted to clarify. And the other thing we tried was, if you take, and this was exactly Ariane's point, can we actually do case steps instead of just one?
Right.
And interestingly, you don't get improvements.
Okay. In terms of the rates, and also in practical. And then in practice, no, right? I mean, because I guess there are constants and stuff like that. I don't know, right? So do you get anything?
I don't know.
You don't know.
In practice, possibly, with respect to the constants, possibly.
So actually, we have one more here. So biological learning rules might have gradient forms, but could be more general, such as more local. Are there some key properties that we might be able to use in analyzing these more general learning rules? So this is actually Zach again. So maybe Zach, do you want to unmute yourself and
There's a lawnmower right outside my window, so I'm afraid it's going to be really loud.
Okay.
Did you say biological learning rules?
I mean, we could just hear you kind of well if you don't mind.
Okay, yeah. So plasticity in the brain, some people try to argue that it's gradient based, but that requires a lot of information moving around. So if you have a more general, let's say a local plasticity rule in a network, you can still view it as some kind of optimization, but it's not a gradient-based optimization. So I'm wondering what kind of key ingredients.
Well, I don't understand why it's not a gradient-based optimization?
Well, for example, if it were gradient, then you would get to.
You're taking local steps here, right? Gradient.
Yes, but you could have oscillations and things like this in the structure. Like there's not necessarily a potential function that you're optimizing. It's just a rule that says how
but these min-maxes are exactly like that. That's why I love them. In optimization, you have this. These are local. I mean, this is also local. Both optimization and this is local because we're taking local.
Yeah, I think it's a different notion of local.
Yeah, I think so. But I want to point out that everything I've talked about, I haven't used the optimal functions. You know, this is not like the gradient methods where you keep making improvement in the function value or in terms of the distance to the optimal solution. This is why these are more challenging to think about because they have these cyclic behavior and all that. So in that sense, it's actually close to what you have in mind.
Yeah, that's true. That's nice. I'll think about that more. Thank you so much.
So let's see. Are there any final questions for Asu? If not, right, I'll just very slowly kind of tune out just in case there's some last minute thing coming on. But if that's not the case, so Asu, thanks a lot for the talk. Again, I learned a lot. I'm guessing a lot of people did as well.
Thank you so much for having me, Santiago. It's great to see you.
Yeah, great to see you. We'll talk to you later. Thank you everyone for joining.
Thank you. Bye.
Bye.